Good morning, students. So, as we move on, we'll take up the module number 1. In the module number 1, we are going to discuss the crystal structure and in relation with the crystal structure, how the material is going to behave. That is a mechanical behavior. Means the properties which are dependent on the crystal structure and how the material is going to behave with those properties is going to study in the module number 1. So basically in the first session we'll study about the crystal structure. In that one we study what is a coordination number, what is the atomic packing factor, that is a APF of a simple crystal structure, that is a simple cubic, body centered cubic, face centered cubic and a hexagon closed packed system. And in the next one we'll see what are the crystal imperfections. Imperfections is nothing but a defects. So here we talk about a perfect crystal and here we talk about a defect. The thing is whenever we are going to what you call process a material, we can't ensure the 100% purity in that one. There will be a impurity which are going to present in that one. Due to those impurities, there will be a imperfection in a perfect solid. So in those things we say point, line, surface and volume imperfection. So what are those things? We will discuss in a session 2. And in the session 3, we will see about atomic diffusion. So a diffusion is nothing but the atoms are going to move from a higher concentration to the lower concentration. Okay, so how exactly the phenomenon works and what is the relationship between the concentration and the flux of atoms, which is defined by a fixed laws, and the factors affecting that one, and we are going to discuss few numericals in that one. And once we discuss the basic about the crystal structure, imperfection and the diffusion, so we'll see with all these perfect and imperfections in a solid shell, so how the material is going to behave. Okay, the stress strain curve, okay, how exactly and what are the categories, that's a ductile and a brittle behavior and engineering and nominal stresses. So all those things we are going to discuss. And once we discuss about the stress strain curve, okay, so what are the mechanical property associated with that one? Okay, say for example, ductility, malleability, yield strength, ultimate strength, offset yield strength, all those things we are going to discuss in a session 4. Okay, so let's take a session 1 where we are going to discuss about a crystal structure. Okay, so whenever we talk about a materials, so here our concentration is only to a solid materials. Okay, in the solid material, so the solid material is classified into two categories. One is a crystalline and one is a amorphous solids. So what is a crystalline solid? A crystalline solid is one where the basic structure unit is a crystal. But when we talk about amorphous, okay, so amorphous we won't talk about crystals and all. Here we talk about molecules. Here the basic structure which is available for a amorphous solid is a molecule. So here you can see the arrangement of atom is in a proper way, okay, in a 3-dimensional, and there is a proper number of atoms which are kept in each row and column. But in amorphous, the molecules are randomly distributed. You can see, okay, there is no proper arrangement and all. All right. So next, so there is a regularity in arrangement of atoms, but here there is no regularity in the arrangements. That we can clearly see with the sketches which are provided there. There is a long range order in the structure and there is a short range. There is a lack of a range in the order. So once you take any corner atom from here to wherever you move in any direction, there is a proper arrangement of atoms. There is a range, there is a order, proper order. But if when you take it into the amorphous, there is no proper range in the atoms. So because of the proper arrangement of atoms, there is a high density. The atoms are arranged with the high density and the strength is high due to the proper arrangement. But here the molecules are randomly distributed. So randomly distributed means the density of that one is low. Because of that density is low, the strength corresponding to that one is less. Okay. Again, the arrangement looks like an army parade. You might have seen during a Republic Day, okay, or maybe Independence Day and all. The parade, how it looks, a definite number of army persons will be there in each column and even in the each row, like that. If you move to any column and any row, the number of atoms which are present in each column and a row are equal. But you cannot see the same arrangement in the amorphous. Okay, there is no proper regularity. Okay, regularity in the arrangement of the atoms. So because of this regularity in the atoms, the melting point will be sharp and it's high, because you see the density is more. So whenever the density is more, breaking of that material will be not so easy. It takes up more load. Okay, because of that one, it withstand high temperature. Okay, but if you take the same with the amorphous one, there is no sharp melting, because at this point it may resist more temperature or a heat, but when it comes to this point, there it may absorb less heat. Okay, so whenever it depending upon the arrangement, the melting point of that amorphous solid will be different at a different point. The example you can say in iron, you can see a proper crystal structure either BCC or FCC, and in SiO2 you can't see the same similarity. Okay, when it comes to the arrangement of molecules. Okay, so once to just have a look into this one. So in a crystalline solid, there is a basic structure called a crystal. There is a proper arrangement of the atoms. Okay, there is a long order in the arrangement of the atoms. Because of that one, the density will be more. Because of that one, the strength is more. Because of that one, the melting point is a sharp and a very high. Okay, and in the amorphous, there is no proper arrangement of the molecules. Because of that one, the density is less. Because of that one, the strength is less. Because of that one, there is no sharp melting point. Okay, like that means you can see it here also. So once it starts with the 0 and it goes to the 10. Okay, so even to write the 10, you need a 1 and 0. That is a basic thing, like that. So once it is a crystal structure, if there is a proper arrangement and all, then you can easily say like there is a strength and a melting point, which again dependent on the arrangement of the atoms. Okay, and even in the exam they can ask like a differentiate a crystal and amorphous solids for 6 marks. At that time you can clearly write all these points with a simple sketch, need not to draw a 3D one. So where you can write a simple repeatable steps in that. Okay, so once you see uh, the crystalline and amorphous solids, so we'll take up the only the crystalline solids here. Okay, so how a crystalline or a crystal structure is made up of. So once you look into that one, you can say there is a atoms. Okay, there are atoms. Okay, which are self-organized. Okay, so even in the previous sketch we have seen the atoms are arranged in a proper way. Okay, and wherever there is no proper arrangement of the atoms or molecules, then those things are called as amorphous. And next, once we see a crystal structure, in that one clearly we see a space lattice. Okay, so in a macroscopic way, we can see a space lattice. A space lattice is nothing but an infinity array of atoms in a 3 dimension, such that each atom has an identical surrounding. Okay, just say for example, if you can imagine a areca nut planting, okay, where they are going to have a proper distance between each atoms. Okay, so one will be here and one will be here, one will be here, one will be here, and a similar way one will be here, one will be here, one will be here, and one will be here. So similar way again one will be here, like that will be having. And if you take any one, okay, say if you take any one object here also, okay, so you can clearly see like so you can clearly see, okay, there is a proper surrounding, that is identical surrounding. If you take this, 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 and this. Okay. So for this atom, so we have 1, 2, 3, 4, 4 atoms which are identical. Okay, identical to each other. So that one we called as a space lattice, where it is going to define by itself with a three-dimensional way. Okay. So now once we move down from a space lattice, so each one, okay, so within the down line we call those things as a unit cell. So in the unit cell, so we say it's the smallest structure which repeats itself, okay, by a translation through the crystal. So how we'll see now. Okay, you can see. So this whole thing is a space lattice. A space lattice is nothing but the number of atoms are arranged in a proper way, okay, in a three-dimensional way, and each one will be having a surrounding equidistant and identical. If you take this atom, this one, this one, this one, this one, this one, this one, this one are identical, okay, identical to this one. So that is what is space lattice. And if you take a unit cell, okay, so this is a unit cell. This simple cube is a unit cell. And if you observe here, okay, so one cube here, one cube here, one cube, and one. So there are 8 unit cells are here. Okay, 8 simple cubes which are arranged. Say now here, one adjacent to the other. So one is here, adjacent to that one is here, and one is adjacent to this one is here, and one is adjacent to this one is here. So these things, okay, are called as a unit cells. Now you might have understood a space lattice is something like a three-dimensional array of atoms, and a unit cell is a basic structure in the space lattice which makes the space lattice. Okay, it is something like a building a home. Okay, so each brick is nothing but a unit cell, and your whole home is a space lattice. Okay, so in order to construct a home that is a space lattice, you need the unit cell in that one. Okay, hope you understood, right? So this is a very important one because all these things are very basic in order to understand the further details. Okay, so now, so we have different crystal structures. Okay, so like a simple one or a body centered or a face centered and all. So basically, so there are like 14 types. Okay, so the one who discovered those 14 types of crystal structure is a Brevis. So these things are called as a Brevis lattices. Okay, there are 14 Brevis lattices. Depending upon this one, again there is a different categories in the crystal structure. So just to take the first one, you can see here. So this is a simple cube. Okay, so we can say cubic crystal here. Okay, simple cube, face centered cubic, body centered cubic, and the characteristic of that one is here. Okay, means whenever we say a cube, all the sides are equal. That is A, B, C are equal, and all the sides are at a 90-degree. All the sides are at a 90-degree. The second category we called as a tetragonal. Tetragonal means what? So all the angles are 90-degree, okay, but two sides are equal. One side is not equal. That is A is equal to B. That is A is equal to B, but C, that is in the x direction, is not equal to the AB. Means if you take the same cube, it is elongated in this direction and this direction. Okay, so you can say like it is taken in this direction and this direction. So in that direction it is elongated. Okay, so that one is a tetragonal. So in the tetragonal again there is a simple tetragonal, body centered tetragonal, and a hexagonal tetragonal. So what are these simple face body centered and all? We'll see in the next coming slides. Okay, just now for a time being you say this is a simple cubic where ABC is equal and alpha, beta and gamma is equal to 90-degree. In the tetragonal, AB is not equal to C, but all the angles are equal. And next category, we'll see orthorhombic. So as the name itself indicates, ortho. Ortho means all the angles are 90-degree, but all the sides are not equal. A not equal to B not equal to C. That is what is orthorhombic. In the orthorhombic, you can say body centered, base centered, and a face centered. Okay. So face centered means in each face, if you take a cube, there are 6 faces. So on each 6 faces, there is a one atom which is shared by 2 unit cells. But if you take a body center, base center, so only the top and the bottom face is having a 2 atoms. Okay, that is a base centered. So body centered means only one atom at the center of a simple cube. Okay, so here A not equal to B not equal to C, and all the angles are equal to 90 degree. So next one we have a rhomboidal. Okay, already we know rhombus. Rhombus means nothing but all the sides are equal, but the angles are not equal to the 90 degree. It will be almost equal to the 120 degree like that. Okay, so that is what all the 3 sides are equal, but all the 3 angles are not equal to the 90 degree. They are equal but not equal to the 90 degree. Okay. So next one we have monoclinic. Monoclinic means all the sides are not equal, only two angles are 90 degree, and one angle is not equal to the 90 degree. In that one we have a simple and a base center. Okay. And the last one we have a triclinic. In the triclinic, all the sides are equal, but all the angles are not equal to the 90 degree. Okay, so it is somewhat similar to the rhomboidal. Okay, so where all the sides are equal, all the side angles are not equal to the 90 degree. Okay, so these are the 14, 3 plus 3 plus 4 plus 4. Okay, total 14 bravices lattices. Okay, so where you can say a simple cubic, a tetrahedral, and orthorhombic, and a monoclinic, a rhomboidal, and a triclinic. Okay, so you need to know the relationship between the each side and each angle, which is defined in the each process. Okay, so these are the 14 bravices lattices. Sometimes they may ask like a explain, okay, or list out the 14 bravices lattices with their relations. Okay, at that time you need to write a simple sketch, and you need to say what are the relation between the sides and the angle. Okay. So as we move on, okay, so once we know what are the basic crystal structure, that is a simple, a body centered and a face centered and a hexagonal closed packed structure. So next will be a coordination number. Okay, coordination number is nothing but the number of atoms, okay, which are nearby and equidistant, we say. Okay, so which are closest neighbor to which atom is bonded, or a very important thing is equidistant neighbors. Okay, so if you take any surrounding, okay, so there should be a equidistant atoms which should be surrounding the atom. So how exactly we'll see. So because of a lattice periodicity, all points have the same number of nearest neighbors. Okay, again the same example. Okay, if you take a plantation, right, so if you have a what you call a number of things here, okay, like this and all. Okay, so the one which is having at this point, okay, will be having a equidistant, this one, this one, this one, and this one. So all these 4 are equidistant. Or if you take this one, this is this one, this one, this one are equidistant. Okay, I can say like now this one, 2, 3, and 4. So this atom is having a 4 equidistant. These are also nearby, but this one is not equal to this one. So we can say this, 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 and this. So these 4 atoms are a neighbor, that is the closest and equidistant. Okay, those things are called as a coordination number. Means the coordination number for this atom is nothing but a 4. Okay. Okay, so that's how exactly we can understand the coordination number. Okay, so now if you take a simple cube, okay, a simple cube is nothing but this you can say is a simple cubic structure. Okay, so this is what we say space lattice, and this one, each one is a unit cell. Okay, you can say this one, so this is a unit cell. Okay. Now, if I take this atom, if I take this atom, okay, so this atom is having a surrounding, okay, so 1, 2, 3, 4, 5 and 6 atom. Okay, you can clearly see it here also. If I take this as a center atom, so this is surrounded by a 6 equidistant atoms. Now you take anywhere, okay, even if you take the atom which is here also, so this is having a surrounding atom. Okay, so this one 1, so this one 2, this is 3, okay, like that it will be here 4 and here it's a 5 and one more which is at this angle will be the 6. So means you take it anywhere, the coordination number for that one will remain same. Okay. Okay, so that is for a simple cube where the coordination number for a simple cube is a 6. So if you take the next one, that is a body center. So this is how exactly a body center looks like. So this is the atom which is at the center of a body, and this one is surrounded by 8 atoms, 4 here and 4 at the bottom. So it is nothing but like a ball which is kept inside a box at the center. Okay, so a ball will be at the center. So 8 corners. So there will be 8 atoms. That is number 8. Okay, this is simple to understand. Next one, so we have a face centered cubic crystal. Okay, here you can see here. Okay, so now if you take any one atom which is at here, okay, at the center, so this atom is surrounded by, okay, so one, wait, okay, so 2, 3, 4 here at the top, 1, 2, 3, 4 at the bottom, and 1, 2, 3, 4 at the mid one. It is something like a, so you have something like this. Okay, so an atom here, alright, so 1 year, 1 year, okay, so 1 year, 1 year. So like this. So 1, 2, 3, 4 like this. There are two, one this side and one this side. So there are total 12 um, atoms which are surrounding. You can see it here. So this red color atom is at the center. So you can see 1, 2, 3, 4. All right. Okay. And like that. So you can have 1, 2, 3, 4 and one more at the 1, 2, 3, 4. So means each face will be having 12 atoms. Okay, so there are 3 which are planes which are perpendicular to each other, and you can have that one. Okay, there is a 12 atoms at the face centered cube. Okay, so the next one is hexagonal closure package system. So hexagonal closure package system. So you are going to have, this is the center atom. Okay, so this is the center atom, and surrounding this one 1, 2, 3, 4, 5, 6. So total 6. So 6 plus these are the 3, 9 plus these are the 3, 12. Okay, simple to understand. So this is the center atom. Okay, surrounding this one 1, 2, 3, 4, 5, 6. 6 plus 3, 9, 9 plus 3, 12. So there are 12 atoms which are going to surround a single atom. Okay, so that's how exactly we can see the coordination number with respect to the each unit cell. So these 4 unit cells are very important for us. One is a simple, one is a body, one is a face center, and one is a hexagon. Just to have a look back into that one. Okay. So a simple cubic structure will be having 6 atoms. Okay, and a body center, a atom at the center, and it is surrounded by 8 atoms. That is a 8. And a face centered will be having 1 atom at the center, and will be having 3 stacks 1, 2, 3. Okay, one at the middle and one to the right and the left, which will be having 4 each atoms. So 4 into 3, that's a 12. And the last one is HCP, that is a 1 atom at the center, 6 atom in that plane surrounding, that is a 6, and 3 above and 3 below. So total 6 plus 6. So 12 atoms we are going to have it in this one. Okay, so this is a very important. So many a times in many competitive exams they will ask like what is the coordination number for a simple cube, or a body centered cube, or a face centered cube, or a hexagonal closed packed for a 2 marks or a 1 mark. Okay, whatever we call as a gate, which is the entrance for a MTech in IITs and NITs and all. There it's a common question. Okay, for a coordination number. So that's how exactly you can remember the coordination number. So next, one more important concept in this session one, okay, before moving on to the atomic packing factor, is a effective number of atoms. So what we said is, whenever we take a cube, okay, a simple cube, we said, so there are 8 atoms at each corner, okay, 1, 2, 3, 4, and 1, 2, 3, 4. But those 8 atoms are not belongs to that unit cell. Okay, so whenever we say unit cell is a small quantity in a space lattice, we said. Okay, whenever we say a small quantity in a space lattice, so if you take this cube, so here at each corner, you can imagine there are 4 cubes, okay, at each corner, and 4 cubes above the things. Okay, just to show here, so we can say, so like this. Okay, so this is a 1 cube, and one more cube, one more cube, and one more cube. And above this one, again, I can place one more cube here on this above, and one more cube here above, and one more cube here above, and one more cube here above. Okay. Now you can imagine, so there is a atom which is in between the first and the second. Means this atom is shared by total 8 unit cells. Okay, understood? So means, so if you have a 4 unit cells at the bottom, okay, so this atom is shared by, total 8 unit cells. So that is what we say, like each corner atom is shared by 1 by 8 into 8. So 8 into shared by 1 by 8. So this 8 will get cancelled, and we are going to have only one atom. Okay, ultimately, so if you take the simple cubic structure, okay, as a 1 unit cell, the effective number of atoms which is present in that unit cell is only 1. It's not a 8. Okay. Okay, understood. That is what we have given here. 8 into 1 by 8 is equal to 1. So there is no number of atoms at the face, number of atoms at the center. So total it will be 8. And if you take the example of a body centered, okay, so how exactly it looks? So it looks something like this. So there is an atom at the center, and there are 8 atoms at the corner. So as usual, for a simple cubic, we said 8 atoms are shared by 8 unit cell. So 8 into 1 by 8. 8 into 1 by 8 we are going to get, and 1 atom is at the center. So that's a 1. So 1 by 8 into 8, that's a 1. So no atom at the face, but there is a 1 atom at the body center. So 1 plus 1 will be equal to 2. Okay, the effective number of atoms which are present in the body center is a 2. You can imagine like so this is my unit cell like this. Okay, so there is an atom at the center. This atom is not shared by any of the unit cell, but the atom which is here, which is here, which is here, which is here are shared by 8 unit cell. So it is a 1 by 8 into 8 plus 1. So it is equal to the 2. Okay, so that's how exactly we can see the effective number of atoms for a body centered cubic. So next one, so we are going to have face centered. Okay, so even in the face centered also, so you can see there are 8 atoms, 1, 2, 3, 4, 5, 6, 7, and one more at the behind. So 1 by 8 into 8 that will remain same. But now at each phase we have one atom. That is, there are total 6 phases. So we have 6 atoms, okay, which are shared by 2 unit cell. That is a 1 by 2 means. So here we are going to have a one more unit cell, something like this, like this. Okay, so now this atom, okay, so this atom is shared by this unit cell as well as this unit cell. So it is a 6 phases, so 6 atoms into 1 by 2, that is equal to 3. The total will be equal to 4. Okay, so that's how exactly we can calculate the effective number. Even though it looks like a 8 plus 6, that is a 14 atoms which are there in the phase center, that is FCC. Okay, but it is shared by 8 unit cells which are surrounding that one. Okay, so it is a 1 by 8 into 8. So 6 phases are shared by 2 unit cells. So 6 into 1 by 2. So totally you are going to get a 4 atoms. That is the effective number of atoms is a 4 in that one. Okay, so the last one is a hexagon closed packed system. So as already we have seen here, okay, so if you take any one atom, okay, so the one which is here, alright, and there is a one more here. These 2 atoms are at the phase, okay, so these 2 are shared by 2 phases, so that is nothing but a 2 into 1 by 2. Okay, so if you keep one more hexagon here, so this atom is shared by 2 unit cell, that is 2 into 1 by 2, that will be equal to 1 atom. Alright, so now these 6 atoms, 1, 2, 3, 4, 5 and 6 atoms. 6 atoms are shared by 12 unit cells. Okay, so means you can say like if I have a one atom here, so I have 1, 2, 3, 4, 5, 6 here and 6 above the one more hexagon. So 12 corner atoms into 6 unit cells. So it is shared by 6 unit cells. So 12 into 1 by 2. So here 6 and there are 6 more atoms which are at this bottom cell. So 12 into 1 by 6. So you are going to get a 2 atoms. Okay. So remaining is, so we have 3 atoms which are at the center. Okay. So that's independent. Those things are not shared. It is enclosed within the hexagon close. So those are the 3. So total here we are going to get a 3. So 2 plus 1 plus 3, that will be equal to 6. So that is what is a 6 here. Okay. So now just to have a look like so 2 phase atoms, one at the top and one at the bottom, which are shared by 2 unit cell. Okay, so that is what we have said here, 2 unit cells. Okay, and 6 plus 6, that is a 12 atoms which are shared by 6 unit cells. That is a 12 atoms shared by 6 unit cells is a 2 atoms, and 3 atoms which are at the center which are independent, that is nothing but a 3. So 2 plus 1 plus 3, that will be equal to 6. Okay. Okay, so that's how exactly we are going to calculate the effective number of atoms in a unit cell. So these two, that is one is a coordination number, where we said an atom will be having a closest and equidistant neighbors, that is nothing but a coordination number, and effective number, even though a cube is having a 8 corner atoms, all those 8 corner atoms are not belongs to a single unit cell. Those things belongs to 8 unit cells. So when we calculate the effective number of atoms to particular unit cell, it's a 1 by 8 into 8. That's a 1. So for a body center, it's a 1 by 8 into 8 plus 1, which is at the center of the body, which is not shared by any of the unit cell. So it's a 2 here, right? For a face centered cubic, it's a 1 by 8 into 8 plus 6 into 1 by 2. That's a 6 atoms at each 6 phases shared by 2 unit cell. So it's a 4. Next, for a hexagon closed packed, it's a 2 atoms at the faces, 2 into 1 by 2, okay, and 12 atoms at each corner, so 12 into 1 by 6, and 3 atoms which are at the center, which are not shared by any of the unit cell, it's a 3. So total it will be a 6. means so these coordination number and effective number of atoms are useful to calculate the atomic packing factor, which we are going to discuss in the next session. Okay, so if you have any doubts and all, you can ask, okay, by sending a message. If not, so we can get it clarified once we are going to start the next session. Thank you.